is a review for Unit 4, Chapter 5, which is System of Equations. Question 1, we need to solve using elimination. And we see that the variables are already lined up here. What we need to try to get is opposite coefficients. So, for example, if I wanted to eliminate y, I wanted to get a negative 6 and a positive 6y. So I'm going to multiply top equation by 3 and the bottom equation by 2. So now I've got 24x minus 6y equals 15. The bottom equation, negative 24x plus 6y equals 14. Now, what happens is the variables cancel out and you get a statement of 0 equals 29. That's not a true statement. 0 doesn't equal 29. There aren't any variables to solve for, so we're not going to get one unique solution. An untrue statement here is an indication that this system has no solution. Question 2, it recommends we solve the system of equations by substitution, and we notice that one of the variables here has already been solved for. We know that y equals 2x minus 3, which also means that this y equals 2x minus 3. So that top equation becomes x minus 3 times 2x minus 3 equals 3. And then distribute the negative 3, combine some like terms, and get x by itself. So we know that x is equal to 6/5. Now, to find out what y equals, we can plug this value 6/5 in for that variable there. So we could say y equals 2 times 6/5 minus 3. And then combining that into a single number 3, if we multiply that by 5 over 5, 3 turns into 15 over 5. So 12 over 5 minus 15 over 5, that's negative 3/5. So the solution is 6/5 negative 3/5. Okay, question 3, one of our application problems. We have a plane that's traveling to Rome and then back. So we're going to reference this formula, distance equals rate times time. What we're going to need to do, though, is set up some variables, because the question is being asked, what's the speed of the plane and what's the speed of the wind? So we need to define variables. I'm going to let x be speed of the plane if there was no wind. And then I'm going to let y be the speed of the wind. Now, since we have a trip to Rome and a trip from Rome, I'm going to use this distance equals rate times time twice, one for each trip. So if we do distance equals rate times time for the to Rome trip, the distance was 880 miles, and the time it took was, let's see, 11 hours. But the rate, the speed that the plane traveled. It was with the wind, meaning it had the speed of the plane, which I'm calling x, and it was assisted, or b, the speed of the wind was adding to the speed of the plane because it was traveling with the wind. So I'm going to add the speed of the wind. So this is the time, and that's the rate. So we have rate times time right there. And distributing that, we have 880 equals 11x plus 11y. Now, that's got two variables, so I can't solve that equation. So I'm going to do another distance equals rate times time for the trip from Rome. The distance was the same, 880. This time it took 22 hours, that's the time. And then the rate, since it was going into the wind, it had the speed of the plane, but it was being made slower because the speed of the wind was going into the wind, so I'm subtracting the speed of the wind. So this is the time right here, and that's the rate, because it's going against the wind. So we have 880 equals 22x minus 22y. So what needs to happen is I combine these two equations then and solve it as a system of equations. So 880 equals 22x minus 22y, and 880 equals 11x minus or plus 11y. If multiplied this by 2 and then solve the system of equations using elimination, I'll be able to solve for x. So I get 880 equals 22x minus 22y, and then 880 times 2 is 1,760 equals 22x plus 22y. I can add these two equations, eliminate the y variable, and get 44x. And then adding those two together is 2640. If I divide by 44, get x equals 60. Now, we have to put a rate on that because x is a speed, and it's in terms of miles and hours, so I know that this is going to be 60 miles per hour. So, very slow plane. So that's the speed of the plane if there were no wind. Now the speed of the wind is my variable for y, so I just need to choose one of my original equations, this one for example, knowing that x equals 60, I can substitute in 11 times 60 now to find my y variable. So 880, that's 660, subtract, and I get 220 equals 11y. Divide both sides by 11, and I get 20 miles per hour. So the speed of the plane was 60 miles per hour. The speed of the wind was 20 miles per hour. So question 4 is from 5.2. This is where we have system of equations with 3 variables, 3 equations. So what I need to do is choose a variable to eliminate first. So I can see here that z would eliminate nicely from equations 1 and 2, so I'm going to combine equations 1 and 2. If I add those together and eliminate z, I get 7x minus y equals 8. So I'm going to do the same thing. I'm going to choose two of these original equations here, but I need to eliminate the same variable that I eliminated in step 1. Since I eliminated z in step 1, I need to do that again. So I'm going to take equation 1 and 2, or sorry, 2 and 3, but I need to multiply equation 2 by 2, so that's going to be 6x plus 4y plus 2z equals negative 4, and then equation 3 remains unchanged. If I add those together, I can eliminate z and get 9x plus 8y equals 1. So now I take both of these and create a smaller system of equations. So if I wanted to eliminate the y variable, for example, I could multiply that by 8. So now, using the elimination method, that cancels. I get 65x equals 65, so x equals 1. Now, going back to one of the equations that only had two variables, now that I know that x equals 1, I can take that equation, for example, and 9 times 1 is 9, plus 8y, subtract 9, and then divide by 8 to get y equals negative 1. And now that I know x and y, I can go to one of my original equations with 3 variables to find z. For example, if I take that one, I know that x is 1, so 3 times 1 is 3, and y is negative 1, so 2 times negative 1 is negative 2. I can solve for z. And you'll recall in class I stated that if we're not solving an application problem, then the solution to a system of equations needs to be represented as a point on a graph. So this is the point 1, comma, negative 1, comma, negative 3. Question 5. Similar. I notice right off the bat that I've got opposite coefficients for y, so I'm going to take equations 1 and 2 as they are and add them together. And eliminate y. Now I'm going to take equation 1 and 3 down here. I'm going to have to multiply equation 1 by 4 so that I can cancel it with that positive 4y. So if I multiply equation 1 by 4, I'm going to get 4x minus 4y plus 20z equals negative 8. Equation 3 is 2x plus 4y minus 2z equals 8. If I use the elimination method there, y cancels, I get 6x plus 18z equals 0. So now, as with the last problem, I take these equations and create a smaller system of equations. That only have 2 variables. So if I wanted to try to eliminate one of these variables, I can multiply by negative 2, and that like this. And if I use the elimination method, what happens is we get a statement of 0 equals 0. All the variables cancel, so there is not going to be a unique solution to this. There's no variables left to solve for, but we have a statement that 0 equals 0. It's a true statement. This is an indication that there are infinitely many solutions. So on an exam, I would need to see this statement that 0 equals 0 implies there's infinitely many solutions. So that's part of it. And like we talked about in class, if there are infinitely many solutions, and if there are 3 variables x, y, and z, the convention, the more common way of writing the solution, because it says we need to state the solution in terms of a parameter t. If there are infinitely many solutions, the convention is to let z be our parameter t, where t is any real number. And then I need to figure out what y equals and what x equals in terms of t. So if I go back to one of the equations that only had 2 variables, this one for example, I can rewrite that now, knowing that I'm letting z be t. I can rewrite this as 6x plus 18t equals 0. And if I solve for x, I'm going to get 6x equals negative 18t. Divide by 6 and I get x equals negative 3t. Now I need to use one of the original equations with x, y, and z to solve for y. So I'm going to choose the middle equation. For example, the middle equation is 2x plus y plus 4z equals 2. If I make the substitutions now for x and z, this is 2 times negative 3t plus y plus 4t equals 2. And I'm solving for y, so I want to get y all by itself. So y is going to be 2t plus 2. Those are the values of x, y, and z, and because this is not an application problem, I need to write my solution as an order, as a point on a graph, so x, y, z, but rather than using x, y, and z, I'm going to write them all in terms of t. So my x term is negative 3t, my y term is 2t plus 2, my z is t. So that would be representing the solution in terms of a parameter t, and I also would be looking for this statement that there are infinitely many solutions. Okay, question 6 and 7 are some application problems from section 5.2. So the question on 6 is how many milliliters of each should this chemist use to make 100 milliliters that's 18% concentrated. So there's 3 acid. So let's let that be our variable. So let x be the milliliters of the 10% concentrated solution. Y could be the milliliters of the 20% concentrated, and Z could be the milliliters of the 40% concentrated solution. So now we need to make 3 equations since we have 3 variables. The first equation we could use is this chemist has to make 100 milliliters. So a combination of x plus y plus z has got to be 100 milliliters. Now, the next thing we could look at is the concentration needs to be 18% concentrated. So we can now use these concentrations. So the first solution is 10% concentrated, so it's 10% concentrated multiplied by the number of milliliters used. The next solution is 20% concentrated, so it's 20% multiplied by the number of milliliters used there. And now the third solution is 40% concentrated, so it's 40% of a concentration multiplied by the number of milliliters used. And we know that it needs to be an 18% concentrated solution. And I see several students on a problem like this for this type of an equation would stop here, but the way a concentration is set up, if you look at the left side of this equation, it's always a concentration multiplied by an amount. Same here, we have a concentration multiplied by an amount, and we have a concentration multiplied by an amount. So we need to have that same setup on the right side of our equation. Here we have a concentration. It's 18% concentrated, but it needs to be multiplied by an amount, and the amount of solution is going to be 100 milliliters. Here's the second equation. The third equation is going to come from that statement there. This chemist has to use 4 times as much of the 10% solution as the 40%. So we're letting x be the 10% and z be the 40%. So I know that this equation is going to contain or deal with x and z. So I'm going to put x and z. This chemist has to use 4 times as much of the 10% solution, or of the x variable. So in order, because there has to be an equal sign in an equation, so it's not true that x equals z, because they're not using, this chemist isn't using the same amount. She's using 4 times as much of the x solution. So because that x solution is already 4 times greater, in order for me to make these equal, I've got to multiply z by 4 in order to make them equal, because x is already 4 times as much as z. So in order for them to be equal in an equation, I have to multiply z by 4. I want to get all the variables on the same side, so I can use the elimination method. So for this equation, I'm just going to subtract the 4z and get it equal to 0. So I'm going to write that as x minus 4z is equal to 0. So now I've got my 3 equations. I can go ahead and start solving. This equation here, or that part, 0.18 multiplied by 100. I'm going to change that to 18, because 0.18 multiplied by 100 is 18. So just to make that a little easier, so this equation right here is already missing the y variable. It's an equation in terms of x and z. So what I'm going to do is combine equations 1 and 2 and try to eliminate the y variable, so that I can end up with an equation with x and z and combine it with this one. So the top equation is x plus y plus z equals 100. I don't really like the decimals in that second equation, so I'm going to multiply that whole equation by, well, really just 10. I can multiply it by 10 to get rid of those, because 0.1 times 10 is just 1, or 1x. 0.2 times 10 is 2, so that becomes 2y. And then 0.4 times 10 is 4, so that becomes 4z. And then 18 times 10 is 180. And then if I make the top equation multiply it by -1, I can make all of those negative. Now but I would need, okay, well, I need to multiply that top equation by -2 now, so I can eliminate y. So this is -2x minus 2y minus 2z equals -200. And the reason I'm eliminating y is because I'm trying to combine it with this equation, that's where y has already been eliminated. So now I can take this equation and combine it with that equation to make a smaller system of equations with just x and z. So x minus 4z equals 0, and -x plus 2z equals -20. If I combine these, x eliminates, I get -2z equals -20, so z is equal to 10. Now that's 10 milliliters of the 40% solution. And it says here in this statement that this chemist is going to use 4 times as much of that for the 10% solution, so I know that x is going to be 40 milliliters. Now that's already 50 milliliters, and this chemist is only going to use 100 milliliters total. So since there's already 50 milliliters being used by the 40 and the 10% one, I know that 50 milliliters is going to be the 20% solution. Okay, question 7. It's a similar type of question. There's 3 types of gas, so I'm going to let x be number of gallons of regular gas and y is going to be number of gallons of performance, and z would be number of gallons of premium. The question is, how many gallons of each type were sold that day? It says total there were 6,500 gallons for that day, so that's going to be all of the types of gas combined. And then it says the total profit there was $20,050. The profit comes from the number of gallons multiplied by the price. So $3 for the number of gallons of regular plus $3.20 for the number of gallons of performance, plus $3.30 for the number of gallons of premium is going to give us our profit for that day. And here we have a similar situation as from question 6. We've got this semi-confusing statement here. There's 3 times as many gallons of regular, which is my x variable, and then premium. So I know it's going to involve x and z. And because I need an equation, there's got to be an equal sign here, but the number of gallons of regular is not equal to the number of gallons of premium. It says there is 3 times as many gallons of regular. So this variable is already 3 times bigger. So in order to make them equal to each other, I need to multiply this one by 3. So now they're equal. And I want to get all the variables on the same side. So I'm going to subtract the 3z. And set it equal to 0. Now, again, the y variable is missing from this equation, so I'm going to combine the top 2 equations and eliminate the y variable so I can add it to that one. So, if I want to eliminate the y variable, I'm going to, well, I've got a choice here. I can either get rid of the decimals or keep them. I'm going to go ahead and keep them in this one. I'm going to need to multiply the top equation by negative 3.2 in order to have an opposite coefficient there for y. So that top equation becomes negative 3.2x minus 3.2y minus 3.2z, and then 6,500 times 3.2 is 20,800, so negative 20,800. The middle equation stayed the same. So now I can add these using elimination method, cancel the y variable. So if I add the x's together, I'm going to get negative 0.2x plus 0.1z, and then subtracting there will give me negative 750. So now I have this equation in terms of x and z. I had this equation in terms of x and z. I'm going to combine them into a smaller system of equations. So if I wanted to cancel x, I could multiply this by 0.2 to get 0.2x minus 0.6 z equals 0. Now x cancels, and I get negative 0.5z equals negative 750. So divide by 0.5 and I get z equals 1,500. So that's 1,500 gallons of premium. And according to that statement, 3 times as much as that was sold for the regular gas. So if I take 1,500 and multiply that by 3, you get 4,500. So I know that there was 4,500 gallons for regular. There was only 6,500 gallons sold total, and these two combined is 6,000. So that leaves 500 gallons. For performance. Okay, question 8 is from 5.3. We're writing the partial fraction or finding the partial fractions for this. Because there are 2 factors of the denominator and none of them are repeated, we're only going to have 2 partial fractions. And if we multiply this whole thing by the common denominator, then it cancels here. So on the left side we just have 7x plus 7. The x minus 5s would cancel there, so then the a would multiply with the x plus 2, and then the x plus 2s would cancel there, so b multiplies with x minus 5. Now I've got this one equation here with a couple of different things. I got an x variable, an a variable, and a b. I'm not solving for x, so I'm not too concerned about x. I'm solving for a and b. And because it doesn't matter what x equals, you can actually let x equal, in this equation here, you can let x equal certain values. For example, if we let x equal -2, and I plug that into there, that becomes 0, canceling out a, which is nice because that would allow me to solve for b. So I'm going to go ahead and stick with -2 and plug it in for all the x's. That gives -14 here plus 7, which is -7. It cancels a there because it's 0. And then -2 there minus 5 is -7, and then multiplied by b is -7b. So that tells me that b equals 1. Now if I do a similar thing, I'm going to let x equal 5. This is what are called convenient values. If I plug a 5 in there, then that cancels b, allowing me to solve for a this time. So I'm going to let x equal 5, all the x's. So here that'd be 35 plus 7, which is 42. Here 5 plus 2 is 7, and then 7 times a is 7a, and then if I plug in a 5 there, b cancels to 0. So we get a equals 6. So then I know what a is, I know what b is, so my partial fractions become 6 over x minus 5 plus 1 over x plus 2. Question 9, there's x minus 1, and then x minus 2 is repeated twice, so there's 3 factors in the denominator, so that means I'm going to have 3 partial fractions. X minus 1 just appears once. X minus 2 appears twice, so what we talked about in class is if we have repeated factors like this, you have to write them kind of ascending. So x minus 1 or x minus 2 to the first power, and then x minus 2 to the second power, and you stop writing it as soon as this power matches the number of times that it's repeated. So that's the form of the partial fraction. Now we do the same technique as from the last example, multiply by the common denominator. So if this multiplies all the way over there, then the whole denominator would cancel, leaving just 4x squared. When that multiplies there, then the x minus 1's cancel, leaving a multiplying with x minus 2 squared. When the LCD multiplies there, one of these x minus 2's cancels with only one of these x minus 2's. So then b would multiply with the x minus 1 and one of the other x minus 2's. Now when this multiplies here, the x minus 2 squares would cancel, so c is multiplying x minus 1. So I'm going to do a similar technique by choosing convenient values. I'm going to let x equal 2 the first go around, because that's going to cancel not only a, it's also going to cancel b, because that's going to put a 0 there, and 0 times b is 0. So x equals 2 is going to be a good convenient value. So if this x equals 2, then I get 2 squared, which is 4. 4 times 4 is 16. A and b are gone, so I plug in a 2 over here. 2 minus 1 is 1, and then 1 times c is just c, so we know right off the bat that c equals 16. Here I could let x equal 1, because 1 minus 1 here is 0, so b is gone. 1 minus 1 is 0, so c is gone. That'll allow me to solve for a. So if I plug in a 1 right there, I get 4. And if I plug in a 1 right here, 1 minus 2 is negative 1. Negative 1 squared is 1. And then 1 times a is a. And then b would disappear and c would disappear, because 1 minus 1 is 0. So I know that a is equal to 4. The only one I haven't solved for is b. And I've run out of what I would call here are my convenient values. Because there isn't another factory here that I could plug in a number to make one of those variables a, b, or c disappear. So what happens at this point is, rather than choosing a quote-unquote convenient value for x, you would just choose a random x value. So I'm going to let x equal 0. Now that doesn't cancel any of these, so we have to include a little bit more information. Up until this point, I also know that c is equal to 16, and I know that a is equal to 4, so I'm going to plug all of that in to get this last value. So if x equals 0 here, then 4 times 0 is 0. If a is equal to 4 and x is equal to 0, I get 0 minus 2, which is negative 2. Negative 2 squared is 4, and then 4 times 4 is 16, so that becomes 16. And then I don't know what b equals, but I'm plugging in a 0 right there. So 0 minus 1 is negative 1, 0 minus 2 is negative 2. Multiply those together, and you get 2b. Now here I'm going to let c equal 16 and x is equal to 0. So that gives me negative 16. So then 0 equals 2b, and then b is equal to 0. So my partial fractions are, if a equals 4, then that one is 4 over x minus 1. b is equal to 0. And 0 divided by anything is 0. So that middle partial fraction actually doesn't need to be written. I wouldn't mark you wrong if you put 0 over x minus 2, but you also don't need to have it, because 0 over any other number is 0. c was 16, so this is 16 over x minus 2 squared. For question 10, we're only going as far as writing the form of the partial fraction here. It doesn't want us to go through the process of solving for the constants. So we have x being multiplied by itself. X squared means x times x. So that technically counts as two factors. So I'm going to have a over x plus b over x squared. And then we talked about in class, x squared plus 25 is an irreducible quadratic factor. So with irreducible quadratic factors, your numerator is no longer just a constant like a or b. The numerator becomes a linear expression. So I'm going to write cx plus d over that irreducible quadratic factor. But because it's repeated, I have to do it again. That would be the form of the partial fractions. It would be a nightmare to solve for a, b, c, d, e, and f, so we're not going to do it. And it doesn't ask us to, it just says write the form. So that would be the form. So question 11 would be from section 5.4, solve system of nonlinear equations. So there you could, I guess, do this by graphing. These are kind of tricky to graph, and it's not the most accurate way, so we're going to solve using one of the two algebraic methods, either substitution or elimination. I notice here that I already have opposite coefficients for y squared. So if I added these right off the bat, I'm going to get 2x squared, y cancels, equals 18. So solving that gets me x equals plus or minus 3. So I can now go back and plug in for y, but I have two different values of x, so I've got to do this twice. So for positive 3, I'm going to get 3 squared plus y squared equals 16. So when x equals positive 3 for y, I get plus or minus square root of 7. Now, when x equals negative 3, I'm going to get negative 3 squared plus y squared equals 16. So it's actually same thing there. So what we have here is actually 4 solutions. Going back to this one, we had when x was 3, we got positive square root of 7, but we also got negative square root of 7. Over here, when x was negative 3, we got positive square root of 7, and also negative square root of 7. What is actually happening here is, if we were to graph this, the first equation is a circle. That's a nice circle. The second equation is what's called hyperbola. Looks something kind of like that. So we would have 4 intersection points right there, where they have similar x values here and here, and the same y values there and there. So kind of an interesting graph, and it's interesting solutions. For question 12, I noticed that my y variables here already have opposite coefficients, so I can add these together to cancel y. And over here I'm going to get 6, and you've got to be careful, those are not like terms, so you can't add them together to a single term. You have to write it as x squared plus x. So what we have is a quadratic equation that you're going to want to get equal to 0 and solve by factoring. So I'm going to use this bottom equation to solve for y. And since we have two different values of x, I'm going to have to do it twice. One for x equals -3, and another one for x equals 2. So when x equals -3, this becomes -3 minus y equals -3. So continuing to solve there, if you add 3 to both sides, you get -y equals 0 and positive y equals 0. When x equals -2, you're going to have that bottom equation, 2 minus y equals -3. Subtract 2 and you get y equals -5. So y equals 5. So this solution was when x equals 3, y was 0. And this solution was when x equals 2, y was 5. Okay, question 13. These are from section 5.5, graphing the solution set to systems of inequalities. So for this first one, I'm going to find the x-intercept by letting y equal 0. The x-intercept then is 4. And then if I want to find the x-intercept, if I want to find the y-intercept, I let x equal 0, divide by 2, and I get y equals 2, so I know the y-intercept is 2, and because this is not a greater than or equal to, it's just greater than, there's a dotted line. And I need to know where to shade, because remember, inequalities also have shading, and the safest way is to use a test point. So if I use a test point of 0, 0, and plug in a 0 for x and y, then I get the statement that 0 is greater than 4. Now that's not a true statement, which tells me the test point I chose to plug in, which was 0, 0, is not part of the solution set. So I chose 0, 0. It didn't work as a solution, which tells me I'm shading away from that point. I'm shading the area that wouldn't include that test point. Now, the second inequality, y is less than 1. Since there's no x variable, the equation y equals 1, that's just a horizontal line going through 1 on the y-axis, and since it's not equal to, it's just strictly less than, it's another dotted line going through y equals 1. And less than 1 means we're shading below. So matter of fact, let me do that in a different color. And I'm shading below this one because those are values that are less than 1. And then x is greater than 0. Whenever you have an equation that's x equals a number, that's a vertical line. In this case, it's going through 0. There we go. So there's my vertical line going through x equals 0, and I want to shade greater than, and you know what? That's actually a solid line because it's greater than or equal to, so let's try that again. It's not a dotted line. It's a solid line going through x equals 0, and values that are greater than 0 are to the right, so I'm shading to the right. So it's going to be up to the student to clearly identify the solution set. The solution set in this one would be the region that would contain all three different of these shades. So it happens to be right here. This would be the solution set. It's underneath that horizontal line y equals 1. It's above the black line, the slanted line of x plus 2y is greater than or equal to 4, and then it's to the right of that other color, that vertical line. So this is the solution set right here. So that answers this part of it, find the solution set. The other part is label the coordinates of the vertices. Vertices would be the boundaries of where the shaded region intersects. There's only one. That's the only vertex of our shaded region. So that vertex right there is the intersection of that line and that line. So in order to find the intersection of those two lines, I need to solve as if it were a system of equations, not inequality. So x plus 2y equals 4, when y equals 1 means that x plus 2 equals 4. So x equals 2. So that intersection point there, one of the vertices of our solution set, has the point 2, 1. That's the only vertex, because the rest of this solution set just keeps getting bigger and bigger and bigger. It's called unbounded. If we were to continue to extend these graphs out indefinitely like this, the solution set would just keep getting bigger and bigger and bigger like that. So there's only one corner that we can clearly identify of our solution set. A vertex is a corner of a solution set. So alright. For question 14, I'm going to rewrite these inequalities. So the first one is y is greater than negative 2x squared plus 4. So this is a quadratic, and since this plus 4 is outside of the function, it moves the vertex up 4 units. There isn't anything inside the function moving it left or right, so the vertex just moves up 4 units. The minus sign flips it upside down, so I know the parabola is going to be upside down like that. And the 2 is going to be a compression. So it's going to make the parabola a bit skinnier. What I'd recommend is just plotting some quick points. When x equals 1, for example, if x equals 1, then we get negative 2 plus 4, which is 2. So I know that 1, 2, because of symmetry, there's also a point there. Now, this is greater than and not greater than or equal to, which means it's going to be a dotted parabola. And then I'm going to need to shade. And again, the safest way to determine where the shaded region is going to be is to use a test point. I'm going to use 0, 0 as my test point and plug it in for x and y. And again, I get a statement that 0 is greater than 4. That's not a true statement, so the test point I chose is not in the shaded region for that parabola. So the shaded region would be on the outside of the parabola where that test point wasn't. So that's the shaded region for the parabola, for that parabola at least. Now this other inequality is negative y is less than or equal to negative x squared plus 8. But then if I divide by negative, you've got to remember to flip the direction of the inequality, so y is greater than or equal to positive x squared minus 8. So this is, let's try a different color, a parabola that's moved down 8 units. And there isn't any left or right movement there inside the function, and there's not a vertical compression. And it's greater than or equal to, so this one's going to be a solid parabola. And now we need to figure out where the shading is, so I'm going to use the same test point 0, 0 to figure out the shading. So if you plug a 0 in for x and y into that second inequality, we'll be able to figure out where that shaded region is. So if I plug in a 0 for x and y, I get 0 is less than or equal to 8. That's a true statement. So I'm going to be shading, for this red parabola, I'm going to be shading where the test point was. In that case, it was inside, so I'm shading inside this parabola. And if the line's extended on the parabola, then the shading would... So what we need to identify now is where would the double shaded regions be, and that's what you need to clearly mark if this were a test question. So the double shaded region is outside of that black parabola and on the inside of that red parabola, so it's this region. It's on the inside of the red parabola, on the outside of the black parabola. And if that one continued up, it would be this region right here. That's our double shaded region. Now the location of the vertices would be where those two graphs intersect, right there and right there. Graphs intersect by solving systems of equations, not inequalities, so I'm going to rewrite the system as a system of equations. And solve the system of equations. I already have opposite coefficients for y. So let me add that the right way. Get 3x squared. So it looks like they intersect when x equals plus or minus 2. So I need to solve for y for both cases. So I need to solve for y for when x equals 2. I need to solve for y for when x equals negative 2. So I'm going to use that bottom equation. So when x equals 2, I'm going to get 2 squared minus y equals 8. So y equals negative 4. If we do it for negative 2, I get negative 2 squared minus y equals 8, which means I'm going to get same thing, y equals negative 4. So the vertices are 2 comma negative 4 and negative 2 comma negative 4, and just looks like, graphically speaking, that's about accurate. This is the point negative 2 comma negative 4, and that's the point positive 2 comma negative 4. So those are our vertices. Alright, these last two questions are from section 5.6, which is linear programming. Linear programming, the main point is given some kind of objective function where either going to find a maximum or a minimum value based on a graph of linear inequalities, and then the vertices, the boundary regions of this shaded region, become the vertices that we plug in and maximize or minimize that objective function for x and y. So we've already been given the objective function. All that's left for us to do is graph this system of linear inequalities, find the solution set, and then find the vertices of the solution set, plug each of the vertices into the objective function, and figure out which one of those give us the maximum value. So these first set of constraints, x and y are both greater than or equal to 0, that just tells us that we're dealing with quadrant 1 right here, where x and y have positive values. The next set of constraints, x plus 2y is greater than or equal to 10, we need to graph that. That's going to be a linear inequality. The x-intercept is 10. And the y-intercept is 5. Since it's greater than or equal to, it's a solid line, and we're only going to graph the region that's in the first quadrant. And just shade on that one. And if we use a test point of 0, 0, and I plug in a 0 for x and y, I get a statement that 0 is greater than or equal to 10, which isn't true. So I'm going to be eventually shading away from the test points. I'm just going to draw arrows right there to remind me where the shading is going to be. For the next one, this inequality here, the x-intercept is 8, and the y-intercept is 6. Let's try that again. That's a solid line because it's less than or equal to. Now when we shade on that one, I would use a test point again of 0, 0. That gives the statement that 0 is less than or equal to 24. That's true, so I'm going to be shading towards the test point on that one, which is underneath. So I'm shading underneath this one and above the other one. So the double shaded region would be this region right here. That's the region that's above and below. So the vertices would be that point, this point, and that point. So I have a point of 0, 6, a point of 0, 5, and then that is the intersection of two graphs, and you can find the intersection of two graphs by solving system of equations. X plus 2y equals 10, and 3x plus 4y equals 24. So if I multiply by negative 2 and then add, I'm going to get x equals 4. So I know the x value there is 4. And if I want to find the y value, I can take this top equation and replace a 4 right there for x, and call that equation 4 plus 2y is equal to 10. So 2y is equal to 6, and y is equal to 3. So that would be the intersection point 4, 3. So now I've got the vertices of my solution set. So I need to find the value of the objective function here for all three of those vertices. So I need to find the value of p for the point 0, 6. I need to find the value of p for the point 0, 5, and the value of p for the point 4, 3. So for the point 0, 6, if I plug in a 0 for x and a 6 for y, that's going to be 200 times 0 plus 500 times 6. For 0, 5, it's 200 times 0 plus 500 times 5, and for 4, 3, it's 200 times 4 plus 500 times 3. So this is 3,000. This is 2,500. And here we're going to have 800 plus 1,500, which is 2,300. So we figure out that 3,000 is the maximum, so 0, 6 maximizes our objective function. Okay, last question is still a linear programming. The problem is we have not been given the objective function, nor have we been given these constraints. We got to come up with all of that. So a little more work involved. So the first thing we need to do is figure out what the objective function is. Now, we see a statement there at the end that talks about maximizing, wants us to maximize profit. So our objective function is going to be maximizing profit using the profit statements earlier in the problem about how much money we get from the regular ski and the slalom ski. So I'm going to set up a profit statement here. Well, first let's define variables. I'm going to say let x be let's see, what is it, regular ski? So yeah, let's say let x be the number of sets of regular ski produced, and that y be the number of sets of slalom so then the objective function, since our objective is to maximize profit, the objective function I'm going to call P for profit. We get $25 for each set of regular skis plus $50 for each set of slalom skis. That's going to be our profit. Now, since we're manufacturing skis and we can't manufacture a negative number of sets of skis, our first constraint is going to be x is greater than, oops, try that again, x is greater than or equal to 0, and y is greater than or equal to 0. Now, it says the maximum number of pairs of skis that this manufacturer can produce is 400. So if we take the number of regular skis and add that to the number of slalom skis, that's got to be less than or equal to 400 because the manufacturer can't produce any more than that. And now we can have some statements for demand. Demand for regular skis is at least 200 pairs, so they've got to make at least 200, so x has got to be greater than or equal to 200, and then y has to be greater than or equal to 80 because demand for slalom skis is at least 80, so 80 or more. So those are our constraints that we're going to graph. And we're going to scale this by 50. here we go. The first two constraints, x and y greater than or equal to 0, that just tells us we're going to be staying in this quadrant right here, quadrant 1. X plus y less than or equal to 400. Both the x and y intercepts are 400, and it's less than or equal to, so it's going to be a solid line. I'm only graphing the portion in the first quadrant. And if I substitute 0, 0 as a test point to figure out the shading, I would get 0 plus 0, which is 0, and 0 is less than 400, which is true, so I'm going to be shading underneath towards the test point. X is greater than or equal to 200 is a vertical line. And greater than or equal to means to the right, so I'm shading to the right of this one. And then y is greater than or equal to 80 is a horizontal line going through 80. And greater than or equal to means above. Numbers without greater than 80. So according to all of those shaded regions, I need to be underneath this line here, I need to be to the right of that line, and above this line. So this would be our solution set. It's a bounded solution set, meaning it's got boundaries on all the sides with 3 vertices. That point has an x value of 200, and we have to figure out the y value. That point also has an x value of 200, and we figure out the y value. This point here has a y value of 80, and we need to figure out the x value. Now, going back to this point here, that's an intersection of the line x equals 200, and the other line is x plus y equals 400. So if x equals 200 and x plus y equals 400, then we know that y equals 200. Now this point here, no, that's actually a little bit easier to figure out because it's right on the line where x equals 200 and y equals 80. This point here is an intersection of the line y equals 80 and the line x plus y equals 400. So if y equals 80, then x equals 320. So what we do, as with the last problem, once we have the vertices of the solution set, we figure out the value of our objective function at each of those vertices. So I need to find the value of p at the point 200, 200, the value of p at 200, 80, and the value of p at 320, 80. So if we plug each of those values in for x and y and run it through the objective function, when you plug in the point 200, 200, you're going to get 15,000. When you plug in the point 200, 80, you're going to get 9,000. When you plug in the point 320, 80, you're going to get 12,000. The intent was to maximize profits. This is the maximum profit. So the question was how many of each model should be produced, and the answer is right here, 200 of regular skis and 200 of the slalom.